This is part 3 of the multiplexing experiment. This part deals with code division multiplexing. Multiplexing is used to provide additional capacity over limited transmission facilities. In the wireless world, frequency spectrum is a limited resource. A fairly new form of multiplexing used for wireless systems is known as spread spectrum modulation. Direct sequence spread spectrum, or DSSS, is one form of this type of modulation that has been adopted for use by wireless LANs. That is IEEE 802.11. Additionally, code division multiple access, or CDMA, has been adopted as a radio transmission technology for cellular systems. In fact, as the cellular providers migrate towards more capacity and wireless data, it is expected to be the modulation scheme of choice for all future cellular systems. For CDMA systems, all signals share the same frequency spectrum simultaneously. Each user in this system has a particular spreading code which is known to both the transmitter and the receiver of the wireless communication link. For all their users, these signals appear as broadband noise. The trade-off required for the ability to share the frequency spectrum is that modulated signals for spread spectrum systems have extremely large bandwidths. So I've got Circuit Maker open here, and this is the first circuit, and this is going to show DSSS. So what you see on the far left is a data sequencer, and that data sequencer, I'll take and click on it and look at it. And what it has is it's got, as you can see here, excuse me, address 0001 to 0016, 16 memory addresses. And if I go and change this to binary, what you see is in each memory address I have 8 data bits. We only are going to take and look at the last data bit, so you can see that it starts as 11101 011 00 111 010. So if we actually take and run this, let's take and drop out of that. Let's run this, and when we run it, it turns out, if we look at the output of that data sequencer, what we see is this string of data bits, and again it's 11010 11 00 1111 010. So we want to transmit that. We're going to stop this. Well, first we'll make it smaller. What we do, we'll stop it. We're going to transmit this by taking an exclusive ORing, that data sequence, with another sequence of data. And the difference will be that if we take a look at this guy here, let's run it, and take a look at here, and get the window back. And we see that, let's blow it up, this data sequence, which is commonly called a Barker code for direct spread spectrum sequence, it turns out that it consists of much narrower pulses, and it turns out that actually for this one the sequence is 1011 0111 000, and that's an 11-bit sequence that repeats itself, and once it's done it starts over again, and it is exclusive ORed with the data sequence. So here's the exclusive OR gate here, and then what happens is it is passed through some transmission facility, this wire here, and at the transmitting end, the same Barker sequence, as it's called, is the 11 ones and zeros that repeat over and over again, is exclusive ORed with what's coming over the wire. let's take a look at what is on the wire here. And on the wire, get the window back, what we see is this. Now it may look the same to you, but it turns out it's not. This is a different sequence of ones and zeros, and it's created by exclusive ORing. And exclusive ORing is a logic function. The only time the output of this is 1 is if both the two inputs are different. If they're both zeros, the output will be low. If this guy is a 0 and that's a 1, or that's a 1 and that's a 0, the output will be high. If they're both 1, the output is low. And then over here, we recover the signal. Let's take a look at it. And we'll get the window back. And here we go. So what I'll do is get the original signal way over here. And get the window back. Oh, I don't know why the window's disappearing, but what can you do? Circuit maker has its idiosyncrasies. So here the yellow is the input to the exclusive OR, and the green is the output out of that detection flip-flop at the very end of the circuit. And you can see that they're the same. The interesting thing is that what's happened is as it's transmitted down, and I'll just click on this guy and hopefully get the window back again. As it's transmitted, it has a much faster bit rate, and hence that would mean it would have a higher bandwidth. Okay, so this is what we call direct sequence spread spectrum, if I can spit it out correctly. Okay, now we're going to go to take a look at a CDMA system. So we'll take a look at CDMA 1 here. I'm going to open this and get the entire screen. So what we have here on the far left hand side is again another data sequencer, but now we have something called a Walsh T, which is for transmission, and that data sequencer has a Walsh code in it. So let's take a look at it. We'll click on it and take a look at it, the data sequencer, and what we see is the last bit, and that's the only one we care about. This is 8 addresses. It goes 10101010 and repeats over again. So that's the Walsh code that's used at the transmitter. And get rid of that. And over here, turns out we have a Walsh code at the receiver. And if we take a look at it, and take a look at its data sequence, it's 10101010, the same as at the transmitter. So in a cellular system, it turns out that when the system is set up, a code is shared between the transmitter and receiver, or between the cell tower and the mobile, if you will. And it turns out, as you can see again, what happens, the data sequence gets exclusive ORed with the Walsh code. Over here, the incoming sequence gets exclusive ORed with a Walsh code, and we end up with the results over here. So let's take a look at what is being transmitted, and we have to run it to do that. So let's take a look. Well, let's see what it comes up with anyway. So what we're taking a look at, this is okay. What we're taking a look at is the green is the data that needs to be transmitted. The yellow is the Walsh code, and it turns, well, actually that's not correct. The yellow is the created code out of the exclusive OR. So if I had one more thing here, which let's take and make this smaller. So if I could go over here, let's do shift, and so now we have a blue one. And let's take a look and see if we can look at the window. And let's see if we can see this. Then maybe not too good or easy to take a look at. The blue is the Walsh code, and you can see that it's blue here, blue. So the Walsh code keeps going back and forth, 101010. The green are the data that you want to transmit, and the yellow are the resulting pulses. Now, they may not look too different to you, but you might notice that here the green goes down and there's nothing, but I have a spread of 2 down the bottom here, 2 times. Over here it turns out that I've got a spread of 2 before I get something, and so on. So it turns out that this was not a super complicated Walsh code. It's a rather simple one. but nevertheless, what it does is work. So I'm going to stop this, and what I'm going to do is go over here. Well, actually, what I'm going to do is take and load up circuit number 2, I think. So let's load circuit number 2. Let's see what we have with circuit number 2. We'll open it. And we don't want to save anything. And we'll take and run it. So let's see what this shows us. And what we're looking at, the yellow is over here. The green is what's being transmitted, and you notice the yellow and green do not match. Well, let's take a look at why that might be. So let's take a look and go to, we got to stop it, and we'll go here to this sequence, the transmit Walsh code sequence, and let's see what it is. 0 1 0 1 0 1 0 1 0 1 0 1 0. Okay, that's what it was before. Let's go over here to the receive Walsh code. And the receive Walsh code turns out to be 11000011. Well, that's not the same thing. So it turns out that what's happening is what I'm getting is an output here. We'll run it again. That's the yellow. It is not what I transmitted. Okay, because I have a different Walsh code here. Let's go back to the last circuit. And let's see, we checked it before, we had the same Walsh codes. So let's go back and let's take a look at this guy. Well, let's run it and we'll take a look at the various signals. And so here is our output. So I'm going to go and click on that, the blue one. I'm going to get rid of, I don't know if I can get rid of this guy here. Okay, I'm just going to take a look at the input and the output. And there we go. So now what happens is you see that when they share the same Walsh code, what happens is we decode things correctly. So let's stop that one. Now the next one is quite the circuit, and this is CDMA number 3, and let's see what happens here. I don't want to save anything. This is a huge circuit, and it turns out that I think you can't make any more parts. A circuit maker would balk at having any more parts. What I've got here is data number 1 and data number 2. Well, data sequencer number 1 and data sequencer number 2. And so these are the data that I want to transmit. And then I've got Walsh number 1 down here. Whoops, don't move. Walsh number 1. My circuit maker is having problems. I'm going to leave that one alone. And Walsh number 2. So what happens is I'm taking and encoding data number 1 up here with Walsh number 1, data number 2 with Walsh number 2. And then, as I've done before, they go into this multiplexer demultiplexer pair. Here's the the transmission facility here, and then I separate them out over at the other end. Notice I have Walsh 1 receive and Walsh 2 receive. So if I run this, let's see what we see. So I'm interleaving the CDMA in time division multiplexing, and I've CDMA'd both of the messages. So this one takes quite a bit longer to take and run. Let's see what we get. Okay, so I'll blow this up, and we have the yellow, which is the output of, that's the data sequence from sequencer 1, and here's the received. So let's take a look at what we have, and we don't have the same thing that's transmitted and received. So again, this is the output of this guy, and there's the output there. So why that is a good question. Let's take a look. Let's take a look at, let's stop this, and let's take a look at the data sequencer. Maybe I goofed it up. The data sequencer here is 10101010. Well, that's okay. That's what we had before. Let's see what the data sequence, rather the Welch code is over here. So here, the Welch code is 10101010. Well, this is not good. Why we're not decoding that is a mystery. This data sequence, let's take a look at the data sequencer here. Let's go and run this again. And it could be that I've got a little glitch in Circuit Maker, so we'll find out. Takes a little while to run, but not forever. So again, we're looking at this guy here and this guy here, and they're not the same. Let's take a look at this guy, the output of this guy, and the output of this guy over here. So let's see what we see. I got to get the window back. And sure enough, they were aligned. So, and they're a different sequence, by the way, you might notice, than what came out of one. Why one isn't working is an interesting question, and I'm not sure that I know the answer to that. Let me go back up here, play with this one more time. This is not the worrisome thing, I don't believe. So here's what's inside there. 1, 1, 1, 3 ones, followed by 0, 1, 0, 2 ones, 2 zeros, 3 ones, a 0, and 2 ones. Well, that's a different code, code than ones down below, that's for sure. But the problem is, and let me just play with this a little bit. Maybe what's happened is, is the problem. I don't know if you can see that, but what's happened here is this has gotten connected, and we don't want that. So there's always a reason why these things happen. And when I dragged that before by accident, I really didn't drive it by accident, but it drove went by itself. That one got connected. Okay, so I think what's going to happen now is if I take and run this, let's run it, and this time I think we should see the same output up the from the top as the input from the top. Can only hope. I got my fingers crossed. Okay, but you want to remember what we're seeing here is the bottom. I've got to make it smaller somehow. Drag it down. No, that didn't help. Drag it down now. I should be able to make it smaller. No, I got rid of it totally. So now what I want to do is I want to go up here and take a look at this. Click on that. Then go over here, the output. This should be, again, now the other code. And of course, I get the window back. And here we are. And it may not be obvious to you, but again, this is a different sequence that we had down the other one. So what we have here is a combination of, no, that's not going to bring this all the way back down. What we have is a combination of CDMA created here, and we interleave them on a time division multiplex system here. We uninterleave them and decode them here and here, and they are correct. If I went and took and changed my, one of these Welch codes here, well, let's do this guy again just to show you. If I go and I'm going to stop this, and remember the Welch code over here is, I think, well, let's find out what the Welch code is. The Welch code here, I should remember it, but I'm not positive. So it's 10101010. So let's say OK, and let's go over here and let's change the receiver Welch code to the incorrect one. So edit data sequencer, and let's just take this guy here and make the last one, or last bit, into a 1, and hit OK. And now what happens is it's not the same sequence we had before. I'll hit OK, and now what I'll do is run this, and we should have the correct A and B locked in from the last time, I hope. We'll find out. Again, takes a little bit of time to run it. And we're almost there. And the oscilloscope's hiding down here. Yeah, indeed. Notice that the green's the input, the yellow is the supposed output, but it is not the same thing. So unless the two systems, the transmitter and receiver, have the correct code, they do not work. Waltz code's a little more complicated than we want to get into here, but it turns out that the Waltz codes I used, I think there's 64, actually 8 of the Waltz codes. I had 8 bits, so there's 8 Waltz codes. And that's it for CDMA.